All right, so another quantity that is important to define here is that of total momentum, which is the sum of the momentum of all the bodies in your system. Here we have a system composed of three particles, right? Each one has a momentum, and we define the total momentum as P1 plus P2 plus P3. So these are vectors, so you would have vector 1 plus vector 2 plus vector 3 added together. So now we are going to talk about one of the most important theorems in physics, which is that of conservation of momentum. It says that if there are no external forces acting on a body, the total momentum before and after the event is conserved. So here we have two particles, right? So they are coming at each other and they collide, right? So during the collision, all the forces acting are internal forces. That means particle 1 is acting on 2 and particle 2 is acting on 1, but there is nothing external acting on these two particles. Therefore, the momentum that you have before is equal to the momentum that you have after. That is because of Newton's second law. The impulse due to this force cancels the impulse due to this force because they are an action-reaction pair. So the conservation of momentum says that if you have a closed system and nothing acting on the system, no external agents, right? So there's no forces on the system, then the momentum, the total momentum of all the particles of the system will be conserved. That is because all the forces are internal forces, they come in pairs and they cancel each other. So let's look at how to write the conservation of momentum. So we have the total momentum, and we can define the change in total momentum of delta P, which is the change on particle 1 plus the change on particle 2 plus the change on particle 3. And then we can see that that's going to give you an F net times delta T. And so if then there's no external forces, and external forces can be thought of forces that pull on particles due to agents that are not part of the system. If there's no external forces, if the net force is zero, then this change here is equal to zero. That's the law of conservation of momentum. Another way to write that is that the final momentum equals the initial momentum, and this is the form in which we are going to use this equation more often. So this is a vector equation. So we have a vector equation, one equation for the x and one equation for the y component of our system. So let's look at a simple example. Here we have a 1 kilogram box that is moving at 3 meters per second, and it collides with a 2 kilogram box, right? So, and the 1 kilogram box is sliding, right? It collides and it sticks, right? So they get together. What is the momentum after the collision, right? So let's just write the momentum before. I'm gonna call that P initial, and that is equal to the momentum of the little box, which is 1 kilogram times 3 meters per second, plus the momentum of the big box, which is 2 kilograms times 0 meters per second, because that one is not moving. At the end, we have just one object, right? That object is 3 kilograms, and it has a final velocity. So now we can write these two equations. We can write that P initial is equal to P final, right? So, or we can write, I'm going to write it up here, and we can write that 1 kilogram times 3 meters per second is equal to 3 kilogram final velocity, or final velocity is equal to 1 kilogram times 3 meters per second divided by 3 kilograms. And then you can solve that. And if you solve that, you get that that is 1 meter per second. This is basically the recipe to solve conservation of momentum problem. We have another one here. We have these two students, Sandra and David. They push off each other, and then we want to find the final velocities. We know that initially they have zero velocities. She's 45 degrees, he's 80 degrees, 45 kilograms, he's 80 kilograms. And then finally, she's moving at 2.2 meters per second to the right, and we want to know the velocity of David. So all we need to do is write the conservation of momentum. So we have initial and final here, right? So we have the mass of Sandra times the velocity of Sandra initially, plus the mass of David times the velocity of David. And these two are zero, so this whole thing here is zero, right? So that is equal to whatever momentum, total momentum I have at the end, which is mass of Sandra times final velocity of Sandra, plus mass of David times final velocity of David. So now I can solve this equation, right? I can take this here, that's equal to zero. So from there I can solve for the velocity of David, and then that is 45 divided by 80 times 2.2, and that is minus 1.2 meters per second. And it's negative because it's going this way, and she's going that way, and we are choosing our x coordinate to be positive that way. So these type of problems are known as explosions. Basically, it's the type of technique that you would use to find how rockets move. And if you have here initial momentum equals zero, then you expel this piece with a momentum pg, then this guy is going to have a momentum pr, and then you know that by conservation of momentum, they have to be equal to zero, and from there you can find the velocity of the rocket. So let's do one more example, recoil. So we have a rifle, right? And the rifle is shot. And so we want to figure out the recoil speed, right? How this speed going back here. So the ball is 30 grams and is fired from a 1.2 kilogram spring loaded toy rifle, right? So you have a ball here and then you have a spring, and the speed that it comes out with is 50 meters per second. So we want to find this recoil speed here. So all we need to do is write our conservation of momentum. So the initial momentum is zero because nothing is moving, so that's this guy here. Final momentum is mass of the ball times velocity of the ball plus mass of the rifle times velocity of the rifle. This is what we want, that number there, so we can do some algebra to solve for that. That's what we want there. And we put the numbers and we find that that is minus 0.38 meters per second.